All right, let's talk a little more about fractions and then get into fractions involving modules. So we defined S inverse A in the last lecture. So now let's do a few more definitions. We actually have a proof in here, but it's like one line. So there's really not really much in the way of proofs in this. Anyway, so in our definition of S inverse A, we chose A to be just a commutative ring. So if A is a domain, then if we let S be the set of non-zero elements, then that's closed under addition, because you can't take two non-zero elements, multiply them together, and get outside of the set, because that would mean you'd get zero, and that means that these would be zero divisors, which you don't have in a domain. So therefore, this is closed under multiplication, which means that it's closed under multiplication and it has 1 and it doesn't have 0. And in this scenario, we call S inverse A the field of fractions of A. And we call it that because it's a field. Because A over S inverse equals S over A, just like you would do in the rationals. And this works in this scenario because let's see here. We know A is, so because A here so here A over S is not equal to 0. Obviously, for it to be you can never invert the 0 element, but you call it a field if all the non-zero elements are invertible. So the fact that A over S is non-zero implies that because we're in a domain, this implies that, well, not because we're in a domain, but in any case, A is not 0. Because if A were 0, then this would be 0 over S would equal 0. So A is non-zero, therefore A belongs to S, and so we can put A in the denominator here. And then S is in S, which is a subset of capital A, and so we can put in the numerator here. So this element is indeed in S inverse A, and if you multiply S over A times A over S, you'll get 1 over 1, which is the multiplicative identity, and so therefore this is the multiplicative inverse of that. So anyways, we'll write this as Q of A, maybe. I'll probably just call it the field of fractions. I don't know how much this will come up. Well, not like how much the field of fractions will come up, but how much like this notation would come up. Anyways, given a field K, and if you set your ring to be polynomials in K, then K with this X in parentheses is going to be the field of fractions of A, and we call it the ring of rational functions in one variable. Okay. Okay, well, it's not Q of A, because Q of A is like the field of fractions, so it's a field, and this is just the ring of rational functions. So this is just S inverse A, where S is... Ooh, wait a minute. What is S in this scenario? I did not write this down correctly. I was probably looking at the wrong thing. This is like for one of the first examples that we have in this section. So yeah. Is it a field? Let me check my other notes here. Well, in any case, I have it written here as Q of A. So, I don't know, maybe it works. I haven't thought about this too deeply. It's just one of those things where it's just like a typical like example that you put at the beginning of a section, and then like we're not actually using it in anything, so I haven't really thought about it that much. Anyways, so whatever. If A is not a domain, we could still take S to be the set of elements which are not zero divisors here. Which, I mean, if it is a domain, we're just back to this case. But if not, okay, so non-zero elements which are not zero divisors. I forget our terminology for zero divisors. If zero is considered a zero divisor, that's one of those weird things that comes up in definitions. I forget if we want zero to be a zero divisor or not, but like in terms of definitions. But for this specific use, A is not considered, or zero is not considered to be a zero divisor. Or whatever way it has to work. S is the set of non-zero elements which are not zero divisors. Then we define QA to be S inverse A, and this is the total ring of fractions. And let's see here. You see this word total here. And yeah, okay, no. This isn't local. This is total. There's something that comes later which will be called localization, and there's sort of like the word local in there. So you might think, oh, maybe those rings are local, and they are. But anyways, until we get there, so we've got this thing. Note that for any S inverse A, we have a ring homomorphism. We'll call it J sub S, and you just take A and you map it to A over 1. Obviously, this is a ring homomorphism because, well, if where does it send A times B? It'll send A times B to A times B over 1, which is the same as A over 1 times B over 1. And where will it send A plus B? It'll send A plus B to A plus B divided by 1. And you could write that out as A over 1 plus B over 1, which is JS of A plus JS of B. And then obviously 1 will go to 1, 0 will go to 0. So it's a ring homomorphism. And for every single T in S, observe that JS of T is invertible in S inverse A. It has inverse 1 over T. And we can do that because T isn't so JS of T is going to be JS of T is going to be T over 1, and obviously 1 over T is going to be in S inverse A, and if you multiply these two together, you'll get 1 over 1, which is 1. Okay, we've also got a universal property, and in keeping with tradition of these videos, we're not going to prove it, but if you have a commutative ring B and a ring homomorphism F that goes from A to B, such that for every single T in S, F of T is invertible. Because remember, that's what happens in this map as well. In this case, there exists a unique ring homomorphism F tilde from S inverse A to B that makes this diagram commute. So if you go from A to B through F, it factors through S inverse A. So you can first go to S inverse A through JS, and then you could go down to B through F tilde. All right. So here's a lemma. The kernel of JS is the elements in A where there is such that there's an element in S such that S times A equals 0. So proof is really short. So I guess there should be another thing here. Kernel of A is in the kernel of JS if and only if JS of A equals 0 if and only if A over 1 equals 0 over 1 in S inverse A. And this is equivalent to there existing some S such that S of then A times 1 minus 0 times 1. So A minus 0 is 0. That's if and only if S of A equals 0. If and only if A belongs to this set. And therefore these two sets are equal. Alright, so that's that. Now, for modules. So if we have a commutative ring A and an A module M, and again we have a multiplicatively closed set S, then we can define S inverse M to be, we construct it very similarly, but instead of doing A times S, we do M times S. We mod out by this similar equivalence relation, M comma S equivalent to M prime comma S. And it turns out to be pretty much the same calculations as, like all the calculations here, you do have to verify it. It turns out being almost exactly identical to before. The only thing is that you have to be really careful with what you're doing because, well, I guess A is a commutative ring, so we don't have to like distinguish between like left multiplication and right multiplication in A. But you do need to keep track of when you multiply two elements together, where is this multiplication taking place? Because like when you look at this this equivalence relation, T and S is such that T times this equals 0. This is the 0 element of M. So where is this happening? So S prime times M. S prime is in the ring and M is in the module. So this is the ring acting on the module. Here again, S is in the ring, M prime is in the module. So S is the ring acting on the module. This subtraction here, we have two elements of the module here. So this subtraction takes place in the module. And so this whole thing in parentheses is an element of the module. And then we're taking it and multiplying it on the left here by T, which is in the ring. So again, this is the ring action on the module. And that gives us an element of the module. So you do need to be a little careful of where all these operations are taking place and what these multiplications mean. Which ones are multiplication in the ring and which ones are multiplication where you have the ring acting on the module. But if you like just look at the symbols are almost exactly the same. So anyways, M over S again will be the equivalence class of M comma S, and then we can give it an S inverse A module structure. So not a ring structure, but an S inverse A module structure by, okay, well we need an Abelian addition law. So M over S plus M prime over S prime will be just this thing, which is the same thing it was for the ring. And you can clearly see that it will be Abelian and that you have an inverse given by, the inverse of M over S will be negative M over S. And then the identity will be 0 over 1. And then, yeah, with 0 equals 0 over 1. And for an S inverse A module, you need S inverse A as a ring to act on this module and give you another element of the module. And that works by you take A over S times M over T, and you just kind of combine it together. So again, being careful about where multiplication is taking place. In the numerator here, A times M, A is in the ring, M is in the module, so this gives us an element of the module. S and T are both in the multiplicatively closed subset of the ring, so this multiplication is the ring multiplication law. And so this will give us an element in the ring, and so again we have element in M over element, well, it'll be an element in S because S is closed under multiplication. So we have element in M over element in S, which matches with the set structure that we have here. All right, so we have an S inverse A module. So we started with an A module and we got an S inverse A module by just dividing things by elements in S. And then the other thing is it doesn't have to be an S inverse A module. It could also be just an A module. And the way we do that is we use this natural map J sub S here. Because this is, we just consider like, we consider A as a subset of S inverse A by thinking of A as A over 1. And that gives us a way to view elements in A as elements of S inverse A, and then we act on it the same way we did before. And that works out just fine too. Do you have to check anything here? No, you don't. It just works. So finally, there's one last thing here that's just sort of an observation about going between ideals and modules. So if you have an ideal B, I call it B here because I didn't want to use the fancy A because that would look like the capital A and it would be hard to talk about. So we have an ideal B of A, so a ring ideal. But we can give it an A module structure by just multiplication by A, and this will work fine because it's an ideal. So it's closed under multiplication by anything in the ring. So now we consider like the ideal generated by the image, the ideal in S inverse A generated by elements of the form JS of B, where B comes from this ideal fancy B. So this is like, so what is this? This ideal, this is just finite sums of the form, you take linear combinations where the scalars are in S inverse A, that's where this is, the AI is in A, and the SI is in S. And then, so these are the coefficients and then or scalar multiples of sort of the basis here, which is, I'm not sure if that's the right word, but you could think of it as like linear combinations of these things, these JS of BIs, and those are, here each BI is in this fancy B. So this is all elements of the form JSBI where BI blah blah blah. Okay, and so then JS of BI is just BI over 1, so this just becomes sums of this form. And you can sort of see that the collection of sums of this form is equal to S inverse B, where here we just take kind of like S inverse A, but we restrict it to things of the form like B over S, where B is in the ideal B and S is in the multiplicatively closed set S. And you can sort of see clearly if you have something in here, then anything in here will look like B over S, and you can get that in here by taking by taking n equal to, so this is of course the sum from I equals 1 to n, but I don't usually write out the indices there. So you take n equals 1, SI equal, or S1 equals S, AI equals 1, and BI, or B1 equals B1 equals B, and then you get B over S in this set, so this is contained in here. And now if you have anything in here, then what you can do is you can sort of like take this sum and multiply everything by a bunch of like the SIs, so that you get a common denominator, and that common denominator will be the product of S1 through Sn. And that will be an element of S. And then on the top, you'll have like a sum of a bunch of things. You'll have the sum from 1 to n of, you'll have AI times BI times every single SI except for the ith index. So you'll have like, so if you were to write it, it'd be the sum from I equals 1 to n of AI times BI times the product of all j between 1 and n such that j is not equal to I of Sj. And then because B is an ideal, this will be a finite sum of a number of elements in B, and so this will be in B, and so this will be an element in here, and so these two are equal. And so as S inverse A modules, this ideal generated by the image of B under JS is exactly the same thing as if you were to start with that ideal and just divide everything by s. And that's all we have to say for now about taking fractions of modules.